All right, so we're on 4B.2, expressing linear transformations with matrix multiplication. Remember, this was a 3 parts, and so we've already done part 1, part 2. Now we're on to part 3, which is today. Okay, so part 3 is the notes that you have today. Your little booklet folds in half, and it should be like a perfect little book for us to navigate through. Okay, your matrix multiplication. Our objective is to use matrix multiplication to apply a linear transformation to a specific point. That is our overall objective for part 3. We're going to take some baby steps and learn some skills in between. But by the end of part 3, that's what we should be able to do. Got it? All right. So putting it together. So linear transformations and matrix multiplications go hand in hand. And we're going to, hopefully you can see that pattern once it's all said and done. First, we're going to review linear transformations. So what we did before the break, we're going to get our gears going, get our minds working, and recall what we did before the break, okay? And do some matrix operations. And then we're going to convert to a matrix and see the connection between the two. Got it? Yes? All right. So before the break, we talked about determining the images of points in a plane using coordinate notation, coordinate transformation. Let me hide this, right? Does this look a little familiar? You were given the transformation description, the linear transformation, and we know it's linear because it's in the form of the standard form, ax plus by, correct? So if I gave you transform of coordinate by 4x minus 3y and negative 3x plus 5y, what am I telling you to do? Yeah, keep going. You got it. Exactly. That's what we learned before the break, right? With linear transformations, you're plugging in x and y to find a new x and a new y. It's multiple things happening to that point at a time, right? I am transforming it to the fullest is a good way of looking at it. So remember, if I want to transform 3-2 using the rule 4x minus 3y and negative 2x plus 5y, that means everywhere there's an x, I'm plugging in a 3, and everywhere there's a y, I'm plugging in a 2, correct? Yeah? So let's do it. So we have 4x, that's not supposed to be writing 4, 3. You saw nothing. So we're going to write 4, 3 minus 3, 2, comma, negative 2, 3 plus 5, 2. Ring in bells. And then you're going to evaluate that, right? I'm going to simplify. So 4 times 3 is going to give me 12. 3 times 2 is going to give me 6. Negative 2 times 3 gives me negative 6. And 5 times 2 gives me 10. So where does my point lie now? So what's 12 minus? Yep. So what's 12 minus 6? 6. What is negative 6 plus 10? 4. So my point is now moved from 3-2 to 6-4. No, we're about to recall. Hey, look at you, a step ahead. All right, so that's what we first did, right? Do you remember doing this before the break in part 1? Okay, after we did this, we then said there's a connection to our matrix, right? The connection to the matrix is I can rewrite that in a matrix form and list out my x's and y's. You remember that? Okay, so we're going to model the matrix with negative 1, 3. So if I wanted to write this as a matrix, that means I'm eliminating variables, right? What would that look like? How would I write 4x minus 3y, comma, negative 2x plus 5y in matrix form? So I write 4, negative 3, and then negative 2, 5. Okay. And then we talked about in the next matrix, in your smaller matrix, the 2 by 1, that's where you write your x and your y. And what is our x and our y? So our x and y is negative 1 and 3. Okay. essentially this matrix is representing the exact same thing that we did here. I'm telling you that you're plugging in these X and Y's to each one of these rules to find a new home. So exactly what we did here mathematically is exactly what takes place here mathematically. Nothing changes. The only thing that changed was how it was formatted. Does that make sense? So mathematically, algebraically, I can never say that word. Arithmetically, whatever it is. We're going to continue. We're still going to be doing the same thing. You're still plugging in for X, you're plugging in -1, right? For Y, you're plugging in 3. Do we see that? So we're still going to have 4 times -1. Yeah? And then we're going to plus -3 times 3. That's my first one. Because isn't that what I would have done either way here? Now we're going to repeat it again. But now we're doing the next one. I'm going to do squares this time just because I don't want to mess up myself. So we now have -2 times -1. So -2 times -1 plus 5 times 3. And when I clean this up, I'm now going to have my X and my Y. So cleaning up the math, what is 4 times -1? -4. What is -3 times 3? What is -4 and -9? -4 and -9? 4 times -1 is -4. -3 times 3 is -9. What does that make?
Well, the following students received meet in the cafeteria at this time: Charles Allen Lynch, Melanie Basaliga, John.
All right, so you are going to choose whichever one. Whether you represent it as a coordinate transformation or represent it as a matrix, you're going to go through and transform each one of these points. Okay? So this is going to be important because we're going to come back to this when we get to a part of our notes about matrix multiplication. Because as you can see, we did matrix multiplication, but we did it using what we already knew how to do. It's all coming together. So if I give you 4 to 5 minutes, do you think you can do C, D, and E and check with your peers at your table for your points? Yeah? All right. Ready, set, go. It's been 5 minutes. All right, so C, as a class, what is your transform point of -4, 5? I'm only going to work it out. We all don't say the same thing. So we got what? What do we get? All right. -31/33. Okay. We don't have to work that one out. Okay. What about D? What do we get? Okay. What about E? What do we get? What? 20. Oh, so we got a discrepancy. All right, so let's double check. So remember, this is your X, this is your Y. So we have 4 times 2 minus 3 times -5, comma, -2 times 2 plus 5 times -5. That gives me 8 plus 15. And then that gives me -4 plus -25, which gives me 29. -29. Yes? All right, so we feel good. We remember this. We're okay. Well, we remember what we did and we're okay with the add-on. All right, cool. Now, we're going to move into matrix addition and subtraction, okay? In order to add or subtract two matrices, they must have the same dimensions. Dimensions are what again? Rows and columns. Remember, it's row by column. So it's your number of your rows by the number of columns, RC colon, okay? From there, you will add and subtract corresponding entries, okay? That means if I'm in row 1, column 1, I'm going to add or subtract to the other element in row 1, column 1. Make sense? All right. So we have A plus B. So before we get started, we're going to make sure we identify the dimensions of our matrices. So we have matrix A here. Matrix A is a what matrix? It's a square, and what are its dimensions? 2 by 2. B, what is its dimensions? 2 by 3. And C, what are its dimensions? 2 by 3. Okay? Yes? We're going to do A and C together. So we're going to do the left side together, and you're going to do the right side. Cool? All right. So A plus B. So I'm going to look at A plus B. Well, the problem is A is a 2 by 2. B is a 2 by 3. Uh-oh, what does that mean? I can't do it. There's no solution. And why is there no solutions? The dimensions are different. So we have different dimensions, means that I cannot do the math operation. There's no solution. Okay? So you just think about when you're adding and subtracting expressions, terms, they have to be like terms, right? Same thing with matrices. They have to be the like dimensions. And if the dimensions aren't like, then I cannot combine. All right. Now let's do C together. B minus C. What is B? 2 by 3. What is C? 2 by 3. Can I combine them? Yes. So when we say corresponding entries to corresponding entries, that means I'm the first row, first element. This is my 11, right? Element 11. Then it's going to add to C11. So B11 goes with C11. Does that make sense? So -2 minus 5. So we have -2 minus 5. Then we have 7 minus 3. Then we have -3 minus -1. Now I'm going to go on to the second row. We have 1 minus -3. We have -6 minus 0. And we have 0 minus 6. So my difference matrix is -7, 4, -2, 4, -6, -6. Doable? All right. 3 minutes of you doing B and D. Go. All right, here we go. So, B, what happened? Why is it no solution? No solution because different dimensions. All right, B plus C. What was your sum matrix here? 3, 10, -4, -2, -6, and +6. Easy peasy, lemon squeezy, right? Yep. All right, so we feel good about practice 1 and practice 2. Yeah, we're gonna keep feeling great because practice 3 is even better. Here we go. So we're now at matrix multiplication with a scalar. Okay, so as you can see, there are 2 blanks in your notes, and there are 2 blanks that you need to fill in. So to multiply a matrix by a single number is easy. You are basically distributing the scalar to each element. Okay, so in regular algebra, right, you have a coefficient outside of your parenthesis that you distribute, correct? Okay, in matrix, you have what's called a scalar outside of your matrix that you're going to distribute to each element of the matrix. I don't know why I went over that far. And then you just simplify. How do we feel? Can we multiply? Yeah. Yeah. Okay, I like to call this the Oprah of matrices. You get a 2, you get a 2, you all get 2. You don't know much about Oprah. Back in my day, she used to give shit a show. She gave people things at her show every day. Sometimes you got cars, sometimes you got books, sometimes you got tickets to Disney World. You never know what you were gonna get as being part of the audience. Okay, that was the awesome part. All right, so here's your time to show me that you understand. All right, so A is an example of showing a scalar multiplication with the multiplication symbol. B is an example of there doesn't need to be a multiplication symbol. It's implied. Got it? All right, go. 2 minutes.